And remember, the one in the middle, the 50%, gives you the closest to the normal curve. Now, they will never, like, sometimes they won't be exactly the same on both sides. They may be a little bit off on both sides, but the curve overall will be closest to the normal curve. And the skews always, always follow the tail. Try to remember that part. Okay, then I gave you 11 and 12. Now 11 and 12 just asked you if they were binomial or not. Remember, to be a probability distribution function, probability, we have two things that happen. All our probabilities are between 0 and 1, and the sum of all your possible probabilities add up to 1. That makes it a probability distribution. To make it a binomial distribution, we have to have four things happen. You have to have a choice, yes or no, success versus failure. You have to repeat this for n fixed trials, and each trial is independent, which means your probability, number 3, will not change. And number 4, your x value has to represent all possible outcomes. Sometimes we get a 0, sometimes we don't. If it's in terms of responses, yes, we get a 0. So this one found that 49%, and a good way to figure out if it is binomial is just to walk through your letters here. 49% of households own a dedicated game console. 8 U.S. households are randomly selected. So 8 is your n. You're asking 8 people. The random variable goes from 0 to 8. It represents those that own a dedicated game console. So when you ask them, they're going to say, yes, I own it. No, I don't. Those are their two choices. Success, failure. So we consider our success that those that own the console game. Now remember, the success is the success in your problem. Okay? Does it make a difference which probability is higher? And yes, this qualifies as a binomial experiment. Number 12, you draw 5 cards one at a time. You do not replace the card once it's drawn. What happens with probabilities when you don't replace? They change. So how could I make this a binomial? Just replace it. All I have to do is replace it. I'm still drawing a heart, so I only care, did you get a heart? Did you not get a heart? There's your success and failure. I'm drawing 5 cards. I'm doing this 5 times. I could have 0 hearts, 1, 2, 3, 4, 5. And all I have to do is replace it to make my probabilities remain the same. Okay? Good with that? Okay. And 16, okay? It's okay if you use the C, if you start with the C. We start with the combinations because it doesn't matter what order these happen in. Probability of success, probability of failure. That's what remains. You could use your C or you can use your binomial PDF. This is a probability distribution function. It goes NPX if you don't have the software. The number of trials, the probability of success, start at your 0 and keep changing this. So yes, technically you have 7 different outcomes. And what do those outcomes have to add up to? 1. Remember to be careful about anything with the scientific notation. Your probability has to be between 0 and 1. So if you get something that says 1.28 e to the negative 3, make sure you move your decimal 3 places to the left. Your probabilities can never be greater than 1. Once you get all your probabilities, then what is the probability of exactly 2? Go here. There's your probability. At least 4. These are mutually exclusive. If you're in one, you can't be in the other. So at least 4, add these pieces up. Less than 3, does that mean I count 3? Nope. So add these pieces up. Okay. I could use the at most. At most means then I'm going to count it. What if I said at most 3? Then which ones would you do? 0 to 3. And if you've noticed this situation, if you're going to do at most 3, can't you do 1 minus this guy? Since it's all the other pieces. So you can use your complement for that as well. I know they didn't ask you that. I just threw that one in there. Right. So once you get your chart, it's a lot nicer to figure these guys out. And number 19, kind of the same thing. 56% of men do not look forward to going clothes shopping for themselves. You randomly select 8 men, and you find the probability of the men who do not look forward to going shopping for themselves. That's your probability of success. Notice they used the not word in there. That's okay. That's what we still consider success in this situation. So we're figuring out men who do not look forward to going shopping for themselves. Now, if we did a graph of this guy, it's pretty close. We'd have a little bit of a skew. Not that much, so a little bit to the left. Not a lot, it would be close to the normal, but a little bit to the left maybe. Because our bars on the right, you can kind of see these are a little bit bigger than these, not by much. You can see the cutoff. These are slightly bigger. So you could even look at your table and figure out where your skew is going to be. Do you guys have any questions with this? Was everybody able to do this?
I feel that more than 5 would be nice.
More than 5? More than 5, you can't count 5. So you're 6 through 8. Right? If I say at least 5, that means 5, 6, 7, 8. But more than, I don't want 5. I need it to be more than 5. Don't forget these values are discrete. They're whole numbers. Okay, good. We've been doing. So we're going to make your table with all your outcomes, and we're going to construct a relative, it's like a relative frequency graph. But we're just going to say P of X on the side. I can't make mistakes like that. All right. So let's work 1 through together. So about 60% of cancer survivors are ages 65 and older. You randomly select 6 cancer survivors and ask if they're 65 years or older. Doesn't matter how old they are. They're either going to say yes, they're 65 or older, or no, they're not 65 or older. We're going to construct a probability distribution for our random variable. So, is this binomial? Yep. What is my N? 6. What is my P? 0.60. What is my Q? And my X goes from 0 to 6. So again, now this one lends itself real nice to the table if you prefer to use the table. I don't know, did your table work out okay? I don't know where my table is. Something happened to my table, so. All right. So let's just fill in our probability. Binomial PDF, and we'll fill these in. You have 6, your probability of this being successful, that they are 65 years or older, and fill in your table. Okay, so everybody should be able to fill this in. Okay, so now, it's a probability distribution because all my probabilities are between 0 and 1, and my sum of all my probabilities are 1. It's a binomial distribution because I have these 4 criteria. I perform this a fixed number of trials. They're independent of each other. My probability is not going to change. I have a success and a failure, and I represent my x variable. Okay? Now, when we graph this, this is your relative frequency graph. Same graph. So we're going to give it a title, and we're going to say cancer survivors, age 65 or older. Make sure you give it a title. These are your S values. Okay, this represents the number that said yes to your, are you 65 years or older? Instead of putting your relative frequency on your y-axis, just put your P of x, your probability. It's the same as your relative frequency. And again, you have to start with your 0 over here because you need a bar for each one. Okay, do one graph with me, guys. This way you get the hang of the graph. And again, figure out money. Your highest amount of money is 32 cents, so if you can go by nickels, go by nickels. I say money because don't give me a 0.5 for your 5.05. Okay, and let's keep track of our bars. We had a real small one here. And then 037, 134, 276, 311, 187, and 47. 047. Okay. Where's my skew? To the left. Slightly to the left. Look at my probability. When my probability is greater than 0.5, my tail is to the left. It makes sense that my higher numbers are favorable, right? Because my probability is favorable. Okay. I realize